In this video, we're going to take a look at solving a non-homogeneous first-order linear system of ODEs. So we've learned how to solve differential equations and systems of them when we have just dx dt equals ax plus by and dy dt equals cx plus dy, but there are situations where we might have a constant or some function of time applied to the rate of change functions. So in general, we'll call them f of t and g of t. These could be exponential functions, they could be sinusoidal functions, or they could be constants. But the thing that makes these ODEs non-homogeneous is the fact that we're allowing something other than a term involving x or y to be added. Now keep in mind these are first order, and this method will only apply to first order systems. It's called the linearity principle, and that has to do with the fact that these are first order linear systems of ODEs. And so that's also important that they have to be linear, meaning that it has to be x to the first and y to the first in each of those equations. When these become nonlinear, say you had x squared or x times y in one of these terms, this method would not apply. So this is an approach that is one that we've used before. It's applying the linearity principle. And as long as we have first order linear systems, the linearity principle applies even if we have systems of ODEs. So the linearity principle in general will say, okay, find a homogeneous solution by taking off or reducing the system. Notice that we've just taken off the plus f of t and plus g of t. And we know how to solve this system already by computing eigenvalues and eigenvectors. Then we're going to find a particular solution. This usually involves some sort of guess by taking a look at the structure of f and g, and then by trying to deduce what might be reasonable functions for those. Now, if these get crazy and they get wildly different, this approach may be vastly more difficult. But when those are specifically constants, like let's take a look at this system here, plus 15 and plus 10. If f of t and g of t are 15 and 10, then the system can be solved, and it can be solved fairly painlessly. So let's go ahead and give this a shot. So the first thing that we're going to do is we're going to solve the linear reduction, or the homogeneous reduction. So dx dt equals 4x plus 12y. And dy dt equals 4x plus 2y. So our coefficient matrix in this case are the coefficients of x and y in dx dt, which are 4 and 12, and the coefficients in dy dt of x and y in that same order, which are 4 and 2. We'll compute the eigenvalues and eigenvectors using technology, and we'll come up with eigenvalues of lambda 1 equals 10, lambda 2 equals -4, and the corresponding two eigenvectors. So we know that the solution can be written as the y of t vector equals k1 e to the lambda 1, which is e to the lambda 1 t, times v1, which is the vector 2, 1, plus k2 e to the -4t times v2, which is -3, 2. And of course, we could write these in scalar form, because what we know that's in the capital Y vector are the functions x of t and y of t. So that's this vector here. And then we can distribute and write k1, or 2k1 e to the 10t for distributing to the top component. And then 1k1, or just k1 e to the 10t. And then we add on the two extra terms here, plus, or rather minus 3k2 e to the -4t, and 2 times k2 e to the -4t. So that's a solution to our homogeneous system, the reduced system. So x of t is the top equation, y of t is the bottom equation. Now what we have to get at is finding a particular guess to 4x plus 12y plus 10, and to dy dt equals 4x plus 2y 4x plus 2y plus 15. Okay, well, how do we get at this? Oh, I'm sorry, I have these backwards. This should be plus 15 and plus 10. Double check that, make sure we have that right. There we go, okay? And so when I look at these, when I analyze these, I have to think about what would be a function that I could, two functions that I could add together and add 15 to it and get the derivative of x. Well, the only function that, or a function that might come to mind normally if this was just a single differential equation, is to guess x of t to be some constant. Okay, so we'll just say x of t equals some constant, and maybe I'll call that p for now. So p is just some constant, and y of t is equal to q, some other constant. That way, what I'm adding here is 4 times some constant plus 12y times some constant plus 15. But what's unclear is what would dx dt be? Well, if x of t is some constant, so again, I'm just going to point out here that this is some constant. I don't know what it is. And I know that q is some constant. Then if I take the derivative of a constant, dx dt is 0. And if I take the derivative of y of t, which is some constant, well, the rate of change of a constant is 0. And the reason I picked a constant for these is because now, if dx dt is 0, in this equation right here, I can write 0 equals 4 times x, which is x is some constant p, plus 12 times some constant q, plus 15. Well, this will certainly be able to add to 0. If I had picked some other function other than a constant, then I'd be saying, for example, if I guess this to be an exponential, let me entertain that for just a moment. Let's just say I guess this to be some constant like e to the at. Well, then its derivative would be a e to the at. And the problem that would pose, and maybe I do the same thing here, e to the bt, and so here I would have b e to the bt as the derivative. Well, the problem with guessing a function of time when your non-homogeneous term is a constant is here I would have 4 e to the at plus 12 times e to the bt plus 15 has to equal the derivative of x, which would be a e to the at. And you can see that this is going to pose a problem. Why? Well, first of all, my exponentials are different, so there's no way that those would be able to add up to give me just one term with a single exponent of a. But what other problem that poses is I can't add 15 to the sum of exponentials and expect to just get one term that will be exponential. For example, e to the 2t plus e to the 3t plus 15 is never going to give me just e to the 2t, for instance. So guessing anything other than a constant for these will create a contradiction from the get-go. And that is because I'm going to be trying to add a constant, again, to two exponential terms. Even if they had the same exponent, then I would still be left with a plus 15 on the right, but I don't have a constant on the left. So that said, this is why we're guessing a constant in this case. So let me go ahead and remove all this stuff here, and we'll go ahead and play with the values that we chose for x and y and figure out what do those need to be. All right, let's take these away now that we're done entertaining that idea. And now what we'll go ahead and do is we will look at what dy dt needs to be. All right, so there's dx dt, the equation with our guesses. And now I will go ahead and look at this one, dy dt. Well, dy dt is 0 because I guessed y to be a constant. Now, there's no guarantee this is going to work out, but so far, we can argue that you can find a constant p and another constant q such that when you multiply 1 by 4 the other by 12, add them together, and add 15 to that result, there's going to be some p and q that will allow you to get 0. And at the same time, 0 from dy dt has to equal 4 times the x, which we've guessed to be some constant p, plus 2 times y, which we've guessed to be some constant q, plus 10. And this is just a system of linear equations. So you can think about p as you know, a p-axis and a q-axis, and these are just going to be two lines such that they're going to have an intersection point, and that intersection point is the value of p and q that satisfies both of these equations. Now I can just go ahead and solve this with technology. And I have that off to the right here, so you can see I just entered the two equations in. 0 equals 4p plus 12q plus 10, or plus 15 rather. And my second equation here, and you can see that there's that graph where those 2 points intersect, those two equations intersect, the p-axis and the q-axis, and it tells me that p should be negative 9/4. So p is negative 9/4, and q is negative 1/2. All right, so what does that tell me? Well, that tells me that as long as x of t, or what we should call x sub p of t, that's the particular solution, is equal to p, and is equal to negative 9/4, which we just found. Y particular of t is equal to negative 1/2. That if I have x being negative 9/4 and y being negative 1/2, then that will solve this equation here. Well, 4 times negative 9/4, let's just check this, is negative 9. 12 times plus 12 times negative 1/2, well, that's negative 6. So I have negative 9 plus negative 6 plus 15, and that does indeed equal 0, which is the derivative of that constant. And we could do the same thing down here, 4 times negative 9/4 plus 2 times negative 1/2. That will give me negative 9 minus 1 is negative 10, plus 10 is 0, which is the derivative of q. So now I'm going to piece these together, my final x of t and my final y of t is going to be the x homogeneous solution plus the x particular solution, and y homogeneous plus y particular of t. Well, what was x homogeneous? X homogeneous was 2k1 e to the 10t minus 3k2 e to the negative 4t. So 2k1 e to the 10t minus 3k2 e to the negative 4t, and then plus x particular, which is plus negative 9/4. And down here I will have y homogeneous. Y homogeneous was just k1 e to the 10t minus or plus 2k2 e to the negative 4t, plus the y particular, which is plus negative 1/2. And there are my solutions to this non-homogeneous system. And as long as these are both constants, our guesses should not stray away from constants. Now, things can get tricky if one of them is a constant and the other one is, say, an exponential function, but for now we're just going to deal with our f of t and g of t for the non-homogeneous terms. Those are just going to be constants for us.